Alright, so what I'm going to introduce to you now is linear momentum. So we're talking about that physics could be put into conserved. And the first thing we learned that was conserved quantities, was energy. So we learned about energy, which is a scalar, and energy is measured in joules, which has dimensions of length squared time squared kilograms. Oops, mass, sorry. So the joule is mass, length squared, time squared, and we tend to see it as what? The newtons, meters, right? Because a newton is a kilometer, meter per second squared, and the meter gets this. And so energy is our first conserved quantity, and it's a scalar. And we see energy show itself in work being done, which is force times distance, or parallel force times distance, because it's in the same direction as the distance component. We see it in kinetic energy, where the kinetic energy is 1/2 the mass times the velocity squared. And even though the velocity is a vector component, squaring it removes directional information. And then we have positional components called potential energy. And so we have the potential energy due to your position near the surface of the Earth. So we'll say due to gravity, which is mgh. Or we have position in a spring, which is 1/2 kx squared. And the total energy of a system is the kinetic energy plus the potential energy plus any work done. And in a conservative system, the work done is equal to 0. And so the energy sloshes between the kinetic and the potential. And so this is conserved. And in physics, we say these are conserved because the energy that goes out into work has to go somewhere else. And so this energy moves from one place in the universe to another. And so the assumption is there was an initial amount of energy for the universe, and the things we see are driven by that energy repositioning itself. And later on we'll learn Einstein's energy is mass times the speed of light squared. And we can think of this as a conversion factor for energy. Now, there's more to it than this, but we'll think in these terms. That you also see people say that mass is conserved. You can do this in chemistry experiments, and we'll do it in some experiments or some setups where the mass doesn't leave the system, nor is it converted into energy, so we can add up the mass and make sure it's all still there. The next thing we're going to look at being conserved is linear momentum. And linear momentum is a vector quantity. And it's best exemplified usually by billiard balls. That you have, billiards is a good, whoops, come back here, sorry. There we go. Billiards, pool. When the balls hit each other, they show momentum being conserved. I think we could say the same thing. There's the demonstration of Newton's Cradle, which is the pendulum balls, usually 4 of them attached to strings, and they hit each other, and the momentum being conserved causes the motion to move back and forth through them. And so what we're going to look at is we're going to look at a vector quantity based off of the velocities and mass of these objects. And so we can look at this system. Where we have some velocity and some mass for object 1. and we have some velocity and some mass for object 2. And that total of this system, everything inside of the system, we'll call the total momentum, which tends to get a lower case p. The momentum tends to be. And what we're going to end up doing is we're going to say it is the sum of all the masses times their velocities. And that's the vector version of the velocities. So in this system here, my total momentum initial, I'll put initial because this is the beginning frame, is mass 1 times velocity 1 plus mass 2 times velocity 2. Now what will happen is these objects will hit each other, they'll collide, and they'll ricochet back. And after they ricochet back, they'll be traveling in a different direction at different velocities. And what we find is, with momentum being a conserved quantity, that the mass, whoops, that was wrong, please don't, I didn't mean to do that, that was a very blue screen, there we go, that the mass 1 and its new velocity, and I'm going to prime that to know that it's the final state, and velocity 2, we'll prime that, and mass 2, and so this is final. And so I'll say initial momentum is this, then in final momentum is m1 v1 prime plus m2 v2 prime. And conservation of momentum says that these two things are the same. And these are vector components. And so we want to look at how conservation of momentum manifests itself as it comes up. There's a nice thing, and Newton expressed this also, is we can talk about force in terms of momentum also. If momentum is changing, right, it's conserved quantity in a system, but if I come in and push on the system, if I put an external force, then that's going to change this velocity, and changing its velocity will change its momentum. And so we can say that the net sum of the forces is equal to the change in momentum over time. And this is Newton's second law, expressed in forms of momentum. And this version of Newton's law has a very useful thing for us, is this actually allows the mass to change. Because looking at the change in momentum, we can change momentum and change the force in this way. Well, so collisions are where we first are going to describe conservation of momentum. And if the forces, there are no external forces, then there is no change to the momentum of the system. So we'll walk this backwards. If this is the statement of Newton's second law, remember how I said in the last lecture, the last in-person lecture, that we can start with Newton's law and we can create all the conservation laws, or we can start with conservation laws and we can create Newton's laws. Well, this is the linchpin between momentum and Newton's second law. And so I started by saying momentum is a conserved quantity, but I could take Newton's second law in this form and say if there was no net force, no external force, then there would be no change in momentum, which would describe conservation effects. And so let's look at collisions. And collisions show us conservation of momentum. And so we're going to use the example that I used above, but we're going to put it on a system that we can study. So let's take a train car and another train car. So we're going to have two train cars that are in the process of sitting on railroad tracks. And this one, let's label this A and B. And let me give them some mass here, and we'll show you how. So this will be a mass of, pull up my notes here, and we'll say they're empty train cars. 2 times 10 to the 4th kilograms. 2 times 10 to the 4th kilograms. So 2 times 10 to the 4th kilograms. And this will also be mass 2 times 10 to the 4th kilograms. But this one has a velocity vector of 0 meters per second. This is not moving. This one, though, is moving in this direction at 24 meters per second. So VA is 24 meters per second. Whoops. And so this will be the positive direction. And so this is the before the system. We know at some point they're going to collide. And what we're going to do is we're going to say there's a coupling in it. Right? There's a coupling. And when these come together, the coupling locks. And so afterwards, we have the two train cars, A and then B, moving. And we want to know which way the combined system is moving and with what speed. And so this is the idea in conservation of momentum systems. And so in this case, we'll develop some nomenclature, which I'll go into a little more detail further on. But this is going to be an inelastic collision, because elastic collisions, everything bounces off, and this one, things stick together. Now, in general, it takes energy to stick things together. In this system, the energy of the coupling is minimal compared to the energy of the system. So the couple locks together. In a lot of systems, like chemical reactions, molecule to atom reactions, and atom and molecule reactions, these energies matter. And the energy taken from momentum comes across. In fact, we'll explore this inelastic collisions and momentum and energy together. But for right now, let's just see what happens. These two are going to stick together and they're going to have some velocity. So we're going to talk about the upper frame as being the initial conditions. And so in the initial frame, our initial momentum is mass A times velocity A plus mass B times velocity B. That's our initial momentum. Our final momentum, when they're stuck together, is going to be the mass of the two, mass of A plus B, because they stick together, times the velocity of them sticking together. And so that's our final. Now, conservation of momentum says these two things are conserved. So MAVA plus MBVB, because PI is equal to PF, the initial is equal to the final due to the conservation. Then this is equal to MA plus MBVAB. And my question was to find the speed or the direction that the combined cars are going in. And so here's my conservation law written out, solved for my variable of interest. And my variable of interest is the velocity and the direction it's going. But we know it started with 0 velocity in the B direction. So that term goes away. And this becomes the velocity of VAB is equal to the mass of A, which I'm going to put in now, 2 times 10 to the 4th kilograms, times 24 meters per second divided by, well, there's two of these, so 2 times that is 4.0 times 4 kilograms. Now notice what happens here. You end up getting a mass ratio. The mass of the initial system ratio will be a multiplier to the velocity. The other thing is sometimes you'll get a velocity component that works its way through. But in this case, we only have the solitary velocity sticking out. So we take these, and this is going to give me 1/2 24.0 meters per second, or 12 meters per second. And so conservation of momentum becomes the tool in which we can see the effect of a collision. And in this case, it's an inelastic collision because the system gains mass afterwards. I'm going to do some examples of collisions and momentum before moving on to the next topics.